Hey, here's the promised screencast on calculating the volume of a pyramid whose cross-sections are equilateral triangles using the principle that volume is the integral of cross-sectional area. Here's the problem that was stated in class that I'm repairing today for you. Consider the pyramid whose base is an equilateral triangle with sides of length 8, whose height is 10, and whose cross-sections are also equilateral triangles, perpendicular to the vertical. What is the volume of this pyramid? So let's see how we should set this up. Imagine this is our pyramid. Its base is side length 8 and it's 10 units tall. And we want to calculate its volume. We're also told its cross sections are equilateral triangles, and its cross sections are taken perpendicular to this altitude of the whole thing. And since we're taking cross sections perpendicular to this altitude, which is 10 units long, by the way, if the volume is the integral of the cross sections, we want the cross sections to be written as a function of h. So that's going to be one of the little tricks that we need to do. So the way I'm going to do this, I'm going to first find an expression for the area of a cross section. So here I'm drawing a picture of a cross section, and I'm putting it on a coordinate axis. So this is called coordinatization. And it lets us do analytical geometry. So if our cross sections have side length r, then the coordinates of all the corners are going to be, so this lower left corner is at the origin, the lower right corner is going to be at the point r comma 0, and this point right here, because it's you can drop a perpendicular bisector down, we know the first coordinate is going to be r over 2. We just don't know what the second coordinate is going to be. So that's what we want to do, because area equals 1/2 base times height. And if I can find the y coordinate of this last point here, then that gives me the height of my triangle. We're going to look at this triangle right here. I know this side has length r, this side has length r over 2. It's a right triangle, so this height here, I'm going to call this b and this b. Okay. So b squared plus r over 2 squared equals r squared by the Pythagorean theorem. So b squared equals r squared minus 1/4 r squared. So b squared is 3/4 r squared. So b is the square root of 3 over 2r. That's the height of my triangle in the coordinate plane. That tells me, coming back to this area formula, area is 1/2 the base, which is r, times the height, which is root 3 over 2r. And so I get root 3 over 4 r squared. Okay, I'm going to call that my area formula for the area of a slice based on the length of the side of the slice. Now, remember, we're going to be looking for the area in terms of a height, where we slice. So we're going to have to look for that next. So to find that next, we're going to look at this triangle right here. And it's a right triangle, and we're going to use the idea of similar triangles, that this small triangle up on top is similar to the big red triangle I drew. So that means that there's a proportionality we can write in terms of side lengths. I'm going to do two things next. So I'll look for this side, and then I'll be able to calculate that side immediately from it. Back to a coordinatized picture of my slice. We've got the centroid here. And what we want to find is that in the picture, there's a yellow triangle, and we want to find the length of that side there. I'm going to call this x. And what I'm going to do is I'm going to be a little sneaky. Consider this line right here. This is the perpendicular bisector, just like this is, but starting from this vertex. I'm going to find the coordinates of this point. Actually, what I'm going to do, it's easy to find the coordinates of this point. Knowing the coordinates of this point, I'm going to find the equation of this line. And then I'm going to plug in this point, which is r over 2. And it's going to give me, the equation of the line is going to give me the y value of this. And from that, I can figure out what this distance x is. So let's do all that. So this point right here, it's the midpoint of this line. And to find the coordinates of the midpoint, you just take the average of the x values to find its x value. And then to find its y value, you take the average of the y values. So with that in mind, the average of r halves and r, that's 3/4 r. And the average of root 3 over 2r and 0 is root 3 over 2, or root 3 over 4r. Now, as I'm looking for the equation of this line, y equals mx, and it's y equals mx because it goes to the origin, so the y-intercept is 0. I just need to find the slope. Well, I have this right here. Slope is rise over run. So here's the run, the x value, and there's the rise, the y value. So m equals rise, root 3 over 4r, over run, 3 over 4r. And so I'm going to write this in the simplified form, so the r's cancel, the 3's cancel, and I can simplify this to 1 over root 3. So that's the slope. So the line is y equals 1 over root 3x. So this height here, which I'm going to call, what should I call this? We'll call it y. Oh wait, I already used y. Yeah, well it is. It's y at r over 2. Y at r over 2 is 1 over root 3 times r over 2. So that's 1 over 2 root 3 times r. Now I'm interested in x. X is root 3 over 2r. That's this big distance, minus the small distance we just calculated, and that is 1 over 2 root 3r. So first let me factor out the r. And then I'm going to find a common denominator. So I'm going to multiply the top and the bottom here by a root 3. And so I get 3 minus 1 over 2 root 3 all times r. That's 2 over 2 root 3. That's 1 over root 3 times r. Okay, so that's what I just found. This distance right here is 1 over root 3 times the side length. Let's go back to our original diagram. That tells me what this length is right here. This is, what did I say? 1 over 2 root 3r? No, 1 over root 3r. So this is 1 over root 3 times 8, or 8 over root 3. So the next thing I want to find out is what is that distance there? I've got this set of triangles. This distance is h. This distance is 10. This distance is 8 over root 3. And this other distance here, well, I guess I call that x in the picture. We know x equals 1 over root 3r. So in this diagram, if I can find out what x is, I can figure out what r is. This diagram is important because we've got similar triangles, and similar triangles tell us the following. H over x, the ratio of h to x is the same as the ratio of 10 over 8 root 3. So I can solve this, and that gives me x equals 4 over 5 root 3 h. So now if I know h, I can determine x. We also know x equals 1 over root 3r. So we can put these two things together to say 1 over root 3r equals 4 over 5 root 3 h. Right? So let's solve this for r, and we get r equals root 3 times 4 over 5 root 3 h. Root 3's cancel, so I've got 4/5 h. Now, the area of the cross section at h, right? That's given by my area formula. But r, I can write that in terms of h, that's 4/5 h. So now I'll get a formula for my area in terms of h. So simplifying this, I believe I get 4 root 3 over 5 squared times h squared. So there we go. We're almost there. Let's just review what I did. I found a formula for the area of the slice I get when I take a cross-sectional slice h units down from the top of my pyramid. Now I can integrate those areas through my altitude that's 10 units long. H goes from 0 to 10. And that should give me my volume of the whole pyramid. So setting up the volume is the integral from 0 to 10 of my area, dh. So let me pull out my 4 root 3 over 5 squared. The integral of h squared is 1/3 h cubed. So the fundamental theorem of calculus, I put those limits of integration there. And I'm not subtracting anything when I plug in 0. So there we go. And how does this simplify? Well, 10 to the third is 1,000. 5 squared is 25. So 25 goes into 1,000 40 times. So we have 160 root 3 over 3 units cubed. And there's my volume. Ta-da! Easy, right? See you soon.